Goes like this: design of reward function for multi-objective adaptive using reinforcement learning. So we'll talk about what is reinforcement learning, what is multi-objective, and what are reward functions, and how all these put together we are going to get a module of self-driving car. So I am Praveen, and I'm a part of system simulation team. I am tech lead from Renault Nissan Tech, and Rahul is co-author of this work, and he is also co-presenter today. Yes, go ahead. So this is the reinforcement learning pipeline. So first, let's look at what American thinks of autonomous driving. Around 44% of people think that the idea of self-driving is bad. So what you see here, it's bad. So we'll come to this, how we can relate. If some of you think that the self-driving car idea is bad, this work will give you some idea, and it will give some hope towards the future of self-driving. So let's look at the formulation of problem. So adaptive cruise control, it is like following a lead car on a highway driving scenario. We have some set of objectives for that, which we'll see later. And next we have to create an environment. So when we talk about environment, the lead car and the ego car, along with the other road scenario, it is the environment, and we'll have the agent made of deep reinforcement learning. Next, reward function. So reward function is our mathematical relations which will help your objectives to be put into the deep reinforcement learning agent and drive towards the goal. So basically, deep reinforcement learning is learning based on rewards and penalties. So we'll see that later. Next, creating agent. So here we have an agent interacting with the environment. So we have to continuously observe the environment and act. What is the appropriate action possible for that state of the environment? So we use deep deterministic policy gradient, which is classic algorithm for any of this type of robotics application. Next is training an agent. So we have a simulation environment, and we have an agent interacting with that. So by doing some lot of iterations, we call it episodes, we enable the agent to learn what is the best policy to comply to our objectives. So next is finally validating. Once we train on a certain use cases or certain conditions, we want our control system or the agent to be generalized, and it should be robust enough to use in any of the highway driving application, because it's very critical in automotive, because if your control system is going to make a simple problem, then it is going to cost a lot of lives. So finally, we'll think about how we are planning to deploy along with other modules together. So you can see here, this deep reinforcement learning, we never use any training data set here. It's all about interacting with the environment live and then learning the policy live. So coming to the adaptive cruise control, we have simple statement like cruise control. The car maintains a set speed and automatically follows slower or slowing preceding or lead car without any driver's input. So it's completely longitudinal control, like acceleration and braking. So that control has to be completely taken by the agent now. So here, if we look at the level of autonomy according to SAE, level 1 and level 2 will come under this application. So we have few of the objectives for adaptive cruise control: tracking accuracy, safety, and comfort. So tracking is how closely or how neatly you follow a lead car, and the safety is what is the safe distance you utilize or maintain with the lead car and the traffic. Comfort, we cannot forget about the comfort, because it's important to maintain the comfort of the passenger as well. So we measure the comfort in the form of jerk. Jerk is nothing but how quickly your acceleration fluctuates. The more the acceleration or the heavy the acceleration, your jerk is higher, which is not comfortable for the passenger car or the passengers. So coming to the environment, how we model the environment. First, the lead car. So lead car here, it is just an input to our ego car, which is our car. So here we have modeled it in a simple way, where if you give some acceleration, it responds to it. So output will be like some velocity and position. So we call it transfer function. So we use this mathematical, very, very simplified mathematical relation for this. So here you can see the response, velocity response when you give some corresponding acceleration to the lead car. So next ego car comes. So this is our car. So we have many more objectives in future to line up, kind of adding SOC, etc. So if you see here, this is how we model the battery electric vehicle. So you have a controller, you have motor, battery. So practically this covers all your subsystems in the vehicle. So you can think that this is a very mathematical model, simple model, but it can be like 99% accurate compared with your physical car. So we use this type of models for range estimation, energy optimization studies, and control system optimization. So next is the modeling approach, which is a traditional way of modeling. So same setup, adaptive cruise control setup. You have lead car, ego car, and some of the states like velocity and position is taken. By MPC control is nothing but model predictive controller, which is normally used. They call it optimal, and it gives input to the PID controller, or which accelerate and brakes. So there are some disadvantages to this MPC. So when you put too many objectives into this MPC, it actually crashes, or it takes too much computation power. So you can say that it needs a lot of model coefficients, and it also lacks generalization. Finally, the hardware requirements too heavy, like 3 times higher than the regular PID controller, because of the complex optimization process involved in this MPC. So this MPC we are going to replace with deep reinforcement learning agent, which is going to be a form of intelligence which will take decisions when to accelerate, how to accelerate, and how to brake. So the complete longitudinal control is going to be taken by our reinforcement learning agent. So challenges in multi-objective adaptive cruise control is, like I said, in multi-objective for MPC controller, the computation is very high. When you go for multiple objectives, I told tracking, safety, and comfort. So when you put so many objectives, it actually is difficult for us to give the proper output in a certain amount of time. So the computation requirement is very heavy for this. Next comes data-driven models. So here you collect the data from real driving scenarios, from real vehicles, from drivers, and then you develop a model. But these are not efficient because we may not have all the drivers like experts. So, and the performance of the model is limited because it cannot be generalized. It will work, or it will imitate only the drivers who are a part of this training data. So again, to collect test data or real driving test data, it is going to be very tedious because it involves a lot of money and cost effect. It's not cost effective also. So deep reinforcement learning has been one of appropriate candidate for this type of control problem. So there are people who tried deep reinforcement learning for approaching this type of automotive controls problem. They used tracking and energy as their objective, and tracking and comfort few, and someone tracking and safety. So these were all not very complete when you look at the adaptive cruise control requirements. So here we have put all tracking, safety, and comfort into the system, and comprehensive evaluation on the driving scenarios. So if you look at the literature, they have done only validation on very conservative scenarios where we just follow the lead car. So here we have considered very edge scenarios or critical scenarios which are considered risky and very, very uncertain in real driving cases. So next is DeepRL. So goal-directed computational learning approach by interacting with the environment. So that is what we see. We have the agent interacting with the environment, and by a lot of episodes, kind of trial and error, it is going to learn. So it is simple, like a mathematical implication or mathematically converting the regular learning process, how humans or any organisms run, like how we learn cycling through pain and pleasure. When we fall, we are going to experience pain, so that is a kind of penalty. And when we drive it for a long time, we get some dopamine, which is going to be the positive reward for us. So that is how the evolution of the brain happens from our young age to the till now. So looking at the architecture, so we have agent, which includes the policy, which is the actual mapping between observation and states. And next we have here a reinforcement learning algorithm, which will enable the optimization of policy based on the rewards you would get. So environment is consists of the lead car and ego car and all the disturbances given here. Next is action. So action is very simple. It's going to be the acceleration braking to control the longitudinal dynamics of the car. Our observation would be velocity error. The velocity error, it means between the lead car and the ego car. Ego car is our car. And the relative distance, the jerk level of the ego car. So here the idea is very clear. The purpose is to develop a control to drive safely with good tracking accuracy and also with comfort. So that is our objective. So here we have the entire framework. We observe velocity error, jerk and relative distance. We are going to add, which is the acceleration. So here ideally if you look at this, we would need acceleration and braking, two signals as actions. But here, since this is a battery electric vehicle, we thought we could use one signal which can be split into two, because basically in a BEV we will not have both acting simultaneously. So either we will be applying brake or accelerating. So that simple trick also reduced the number of action. In a way, it also helped us to converge easily. It reduced the difficulty of the problem actually. So next, the rewards. This is very important because the reward tells. So if at all the agent is acting, if that action is very good or not, how bad it is and how good it is. So mathematical function that maps the agent state action pair to a numerical reward. So it's going to be a simple numerical reward based on the action, and it is going to help in coming up with a policy or the optimal policy. That is what ideally we call it optimal policy at the end of iterations. So ideally there are two ways broadly classified. One is sparse reward, the other one is shaped reward. Here you could see it's a step form of reward or a mathematical function. You can assume that if there is a hard constraint or threshold given above which we need to give some reward or penalty, we can choose this. And reward, shaped reward, we can say that it's for any kind of action you will receive some form of reward or some amount of reward which is going to help you towards collecting a higher reward in the future. So the total reward function is how we are putting all the objectives into the reinforcement learning or guiding the reinforcement learning agent. So first we could see the track reward, comfort reward, and then safety reward. So first we'll talk about tracking reward. So it comprises of three components. Depends on the velocity error. If you could see, it's quadratic, and next T1 depends on the velocity error, but it's a positive reward for good tracking. So it's a so next T2. So here in cruise control we also set maximum speed for the car. So if I'm going above the car, above the set car speed, then I will be incurring some amount of negative reward. So that is T2. So you could see that here combination of first component and T1 component. Here this is T2 component. Next is comfort. So comfort can be easily mathematically, you can put in the form of acceleration and jerk. So acceleration, any acceleration, higher acceleration will give you some amount of penalty. You are going to incur some penalty. Again, for the jerk above 2.5, why we took this 2.5 meters per second cube it is the standard as per SAE. So you will get a higher reward, I mean higher penalty for jerk higher than this level. So it's a hard constraint for the algorithm or the agent. So finally we have safety reward. So here if you see starting from less than 20 meters of relative distance, you are continuously going to give some penalty to the agent. So it will try to avoid all these scenarios. So that is how we put safety into the requirement. So this is DDPG learning algorithm. It's complex, but I will try to give you simple intuition. So it is called deep because we have two networks, actor and crediting network. It is basically neural network, so we call it deep. Deterministic because you are going to give one action, single action. It is not probabilistic. Policy gradient because the training process is based on policy gradient approach. Yes. So now we have everything in place. The environment, we have connected the RL agent to train. Now it is important to let the RL agent to interact with the environment for 1,000 episodes. So for 1,000 episodes, we have let the simulations go. So this is the profile, acceleration profile, which we give to the lead car during the training process. So other than this, we also have other adaptive cruise control parameters or model parameters, where you can see some of the parameters are put in brackets, like we have some range. So we initialize each episodes of simulation with different values. We randomly initialize so that the model is generalized. Previous slide. Slim slide. So here you could see that it's a 1,000 episode simulation. So you could see around 500 episodes. It has almost reached close to optimal, and then still some optimization of the policy is happening. So you can see that almost 13 hours simulation, overnight simulations. So here I would like to focus on this hyperparameter discount factor. It tells you about how you are focused on or how much you are sighted, whether you are long sighted or the agent is long sighted or short sighted. For example, higher the discount factor, it focus on rewards in the long term also. If the discount factor is very less, it will focus on the rewards which are only in short term. So that's one of the key factors for all those control system or robotics problems. We use discount factor, which is 0.9, which gives us very good optimized results. So after training, we have this actor network, which is going to act or give the control to the ego car. So this is the policy which we would like to take up and put it into our control system. So now, after training, so we have this block which will look at the states, and then it is going to take proper action, optimal action. We'll see how optimal it is and how generalized it is in our validation. So you should keep in mind that we have only one form of acceleration pattern which was given during training, but here in validation we have a lot of different and dynamic input profiles. Let's see how the vehicle actually drives, or how the agent has learned to drive. So first case is follower mode. Here the vehicle is going to simply follow. We don't have any speed restrictions here. So you can see that the lead car velocity, this is the velocity, and here we have the relative distance, and here we have jerk. So here we can see along with the how the ego car actually tracks the lead car here, and you can also see that the relative distance is perfectly maintained, and it's almost always higher than 20 meters. So we can see in the animation that how closely we track the lead car. So the x-axis in position. So maintaining a distance of 20 meters, close to 20 meters, it is tracking the lead car. Next is this difference between this case and this case is that here you have a limitation in the maximum speed of the lead ego car. So you will see that the lead car velocity is limited because that is the maximum speed which is set by the driver. So here you can see that after the ego car reaches its maximum velocity, is going to cruise at that speed, but the lead car, it is going to go to higher speeds. And finally, we have a braking scenario where my lead car brakes, but appropriately the ego car also brakes and tries to maintain the relative velocity, ensuring safety of the vehicle. So important thing to see the jerk levels. So even though we have given a lot of high level perturbations, the jerk value is very small, which is less than 2.5 meters per second cube. So this is an interesting case because this is one of the highway driving is actually uncertain and very risky. So this is one of the risky situation. First one is cut in. So you are going in one lane and then there is another car coming into your lane. It might reduce its velocity or it can increase its velocity. So the point at A, a new car or the new lead car is going to come in and then it is going to reduce its velocity. So if you see, the relative velocity suddenly came down and the ego car actually maintains and tracks well and also maintains the safety distance well. And here it is cutting in, the new vehicle is cutting in, but the velocity of the lead car is very high. Still the vehicle adapts to maintain or follow the lead car here. So next is cutout. So you have a lead car and then what happens is it moves out of the lane and then you have a new car coming in which is at lower velocity. So if you see, the velocity suddenly decreased because of the new lead car coming into place, and then the ego car actually tries to adapt its velocity and then maintains the safety of the way, ensures safety also, and then the jerk levels are also very minimal or less than the criteria. So this is one of the what to say, a real driving acceleration profile. So very dynamic. So still we are able to track well, maintaining relative distance and then jerk levels. So all the, if you look at performance in all the scenario, it's doing well. So in our work, tracking accuracy, ride comfort and safety, they are all considered and then tested in edge scenarios or risky scenarios like cut-in, cut-out, and then real driving conditions. And we proved to be efficient, robust, and the behavior is also generalized here. In literature, you can check like the jerk levels are very high. So we have tried to maintain, which is phenomenal when you compare with other papers. So we have a few more objectives and few more agents to be modeled. So one is multi-agent for new agent for longitudinal control and lateral control also. So we would like to integrate and then level up in the autonomy skill, and then efficiency we can put SOC or minimum energy consumption as one of the objectives, and then other driving scenarios like traffic, which is really difficult for a driver or we face difficult conditions. So what is the final goal? We want our agents to be intuitive, intelligent, and liberating. So when we say liberating, we would like to liberate our computers to do all the job for us. We'll liberate the computers as well as we will have time for our own liberation. Yeah.